From the beginnings of our solar system 4.5 billion years ago, there remain tantalizing clues to its evolution. Remnant debris, asteroids and comets. They vary in size from grains of dust to mountainsides, from footballs to planetoids. They were the building blocks of the planets and perhaps carry the origins of life itself. Now within our grasp, these rocks of ice and dust are ready to give up their secrets. Asteroids are believed to be made of chondrules, flash-heated grains of rock within the stellar disk of our forming solar system. These chondrules clustered together, forming the first asteroids and the building blocks of the planets. Once the solar system had evolved, there was a lot of asteroid material left over. They cover a broad spectrum of types. The largest of these are minor planets or planetoids, large enough to have an ovoid shape. This category took the previous planet Pluto off the major list and onto the minor. The smallest remnants of debris are often called meteoroids. There are in fact several minor planets. Some have been seconded into planetary orbit and become moons. The traditional asteroid belt between Mars and Jupiter has one called OSIRIS, the largest and the first to be detected. Our first close-up of an asteroid was courtesy of Galileo on its flight through the main asteroid belt towards Jupiter. It photographed 951 Gaspra, an S-type asteroid with an average diameter of just over 6 kilometers. The S stands for stony composition. Galileo then photographed the larger 243 Ida at 15.5 kilometers wide, revealing that it has its own moon named Dactyl. Asteroids are not limited to the asteroid belt between the orbits of Mars and Jupiter. Many orbit much closer to Earth and are known as near-Earth objects, or NEOs.
Radar is a very powerful instrument that we use to study near-Earth asteroids. Asteroid Toutatis was millions of kilometers away, and we were able to resolve surface rocks. We could see boulders.
There are currently only 2 radar facilities in the world that have sufficient sensitivity for doing regular observations of near-Earth objects: Arecibo and Goldstone.
Even the most powerful optical telescopes, and I'm talking even, Hubble telescope, they can only see this asteroid as a point of light. It is just too far and too small.
It provides an extraordinary opportunity to get very detailed radar images.
You are transmitting microwaves. It's propagating at the speed of light toward the asteroid. It is bouncing back. And this radar echo is containing surface features of the asteroid. It's telling us about its rotation, and it's very precisely pinpointing its distance from the radar.
These asteroids were imaged with ground-based radar. BL-86 revealed it has its own moon, and asteroid HQ-124 passed very close to Earth, some 3.25 times the distance to the moon. It is due to return sometime in the 24th century. Scientists are looking much more closely at these objects for their potential to pass through Earth's orbital plane and perhaps pose a threat. The most common type of asteroid is the C-type carbonaceous, accounting for about 75% of known asteroids. The probe near Shoemaker was the first dedicated asteroid probe launched by NASA. It photographed 253 Mathilde, a C-type, then moved on to 433 Eros, the largest visited at the time, where it orbited, took extensive measurements and, more by accident than good planning, landed on the asteroid, the first probe to do so. Deep Space One, an experimental NASA probe, was sent to investigate an asteroid 9969 Braille. Technical errors returned poor imagery. However, the probe continued on to its second rendezvous, for the first time with a comet, 19P Borrelli. Comets are closely related to asteroids, but originate from the cold, dark outer boundaries of our solar system.
Comets are bodies in our solar system that have been left over ever since the solar system formed, some 4.5 billion years ago. And therefore, when we look into comets, we look into the past of our solar system. And so by investigating the details of comets, how they formed, how they evolved, we can actually have a glimpse into how our solar system formed, and in the end, how the Earth formed and why we are here.
Comets have been recorded throughout history, as they are easily observed when close to the Sun, often considered an omen. One comet of note was Halley's. In 1986, Halley's comet returned once again, and this time it was met with a veritable armada of space probes. The first attempt at a space rendezvous was with the International Comet Explorer, or ICE. It passed through the tail of comet 21P Giacobini-Zinner on its way to meet Halley. The European Space Agency sent Giotto. The Russian and French sent two probes via Venus, Vega 1 and Vega 2. Japan sent Suisei and Sakikage, that country's first deep space probes. Their measurements went on to refine the targeting for Giotto to make a much closer pass of the comet's nucleus than first planned. In 1994, astronomers and scientists were given an unexpected treat. Comet Shoemaker-Levy broke apart and struck Jupiter in a spectacularly violent fashion. Comets required more study. The Stardust probe was dispatched to investigate 5535 Anne Frank, Wild 2, and then the Tempel 1 comet. It returned a sample of cometary tail to Earth.
Our biggest discovery that we did was looking at this cometary material that was returned from NASA's Stardust mission. And the Stardust mission went up, rendezvoused with a comet, brought back very small amounts of material, comet material and comet exposed material. We had basically one shot at looking at this, and it was really pushing our limits of detection. So I spent about 2 years optimizing our technique, really rehearsing, practicing, getting everything as perfect as possible before the one day of doing measurements. It's sort of all leading up to one big game, one big day. And also just working with meteorites and working with the cometary material, I'm working with something that's 4.5 billion years old that very few people ever get to play with, and the few days of being able to do the actual measurements make up for all of the rehearsals that it takes.
JAXA launched Hayabusa to study asteroid 25143 Itokawa and to retrieve a sample from the surface in a touch-and-go maneuver. The mission took a total of 7 years to accomplish, with the sample return pod retrieved from the Australian outback in 2010. Launched a year earlier by the European Space Agency was a very ambitious spacecraft called Rosetta. Its goal? To land a probe on a comet, 67P Churyumov-Gerasimenko. Just getting there was to prove a challenge in astronavigation.
But when you want to rendezvous with a comet, you have to accelerate the spacecraft and match the same velocity that the comet has around the Sun. So this is the problem, not only the distance, but also the velocity. There is no rocket that can give us the velocity needed to be as fast as the comet. Like close to a planet, and you use the gravitational attraction of the planet to actually accelerate your spacecraft.
It passed by asteroids 2867 Steins and 21 Lutetia.
Lutetia is a very strange target, a very strange asteroid. We believe that it may be a C-class asteroid, which means that it is very primitive. However, it shows from ground-based and also spaceborne observations that Lutetia does not look completely like a C-type asteroid, and we are really puzzled about what it really may be.
The spacecraft then moved on to its primary target, Comet 67P.
The nucleus is pulling the spacecraft out of its planned orbit, and that can be seen as a shift in frequency of the transmitted radio signal from the spacecraft. And the extent of this frequency shift is a measure of the mass of the comet nucleus, so we are able to weigh the nucleus here.
There is no ice at the top, so it's covered by a mantle that we consider is essentially made of organic material. That's why it's very dark. And this material is one of the key things we would like to explore and analyze.
These organics may hold the secret to life on Earth.
What it's all about is the carbon chemistry. How much did the comets bring to Earth? So was it just the right elements, the right building blocks, or was there more information in it when these comets already arrived?
To try and answer these questions, ESA attempted one of the most daring missions mankind has ever undertaken, to land a probe on the surface of the comet. Landing on a comet is one of the hardest things that has ever been done by the human species.
This is the comet. It's roughly a 1 in 1,000 model, so the real thing is 1,000 times bigger. The landing site is roughly here, which we're aiming for to deliver the lander. It's the flattest part we could find. What we are studying at the comet with the instruments are basically what are the ingredients, which materials are present, and coming back to one of the objectives of the mission, how complex are the materials present at the comet.
Landing means flying very, very slowly over the comet and then gently pushing away the lander. It's not a landing like you can imagine on the moon, where you come with rockets and you have to brake. Here the problem is the opposite. You have to really touch gently the comet. The forces involved are very small.
If I get meaningful data, that would be just marvelous. If the descent works, the landing is okay, we receive a sample, and the whole thing runs smoothly, that would be just great. But we need a lot of luck, really. And we had a lot of luck already.
So we are sitting on the surface, Philae is talking to us, more data to come and to be analyzed right now. Going down, which it should do, of course. We are there, it's done its job. We are on the comet.
The science has started now. We have the first results that give us the first comprehension of what we think the comet is, where it started from. Now, for the rest of the year, we'll watch how the comet evolves. We'll unlock how the comet works. We're looking at where the gas and the dust start to accelerate from the surface and how that beginning of the coma, that birth of the coma works. So how the coma develops as it does to higher altitudes. This region has only ever been theoretically constrained or modelled. These will be the first measurements we make in this area or this region, and that's a really big, important target for us.
Eventually, the tiny probe shut down.
Having Philae reactivated is not so likely, but it's not impossible. Philae was designed to hibernate, was designed to switch off and be able to reactivate itself. Of course, we expected this to be a duration of a few days or a few weeks, not a few months. But okay, we will see. Maybe we are lucky and the units have survived these months and will reactivate in June, July.
While observing the asteroids, scientists were surprised to find one with what looked like a cometary tail. After careful study, scientists realized they were observing the results of the impact of 2 asteroids. 596 Sheila had been struck at high speed by a small asteroid. The impact hit with the force of a 100-kiloton nuclear bomb. NASA had done something similar with Deep Impact, a probe sent to Comet Tempel 1, where it dispatched a kinetic impactor which struck the comet to study the impact and the debris thrown up as a consequence. Soon after, NASA launched another small ion-powered probe, Dawn, which also had an extraordinary mission: to travel deep into the asteroid belt between Mars and Jupiter. Its targets, two of the largest asteroids in the solar system. Dawn rendezvoused with 4 Vesta and orbited it for over a year, returning a wealth of data. Dawn then departed and cruised towards OSIRIS, the largest of the asteroids, a planetoid, where it has obtained orbit and begun its study. JAXA, the Japanese space agency, has recently launched a second Hayabusa probe, this one with many improvements over the first. Its target is the C-type asteroid 1999 JU3. It's expected to reach its destination in 3 years, collect samples, and return to Earth by 2020. NASA has announced the OSIRIS-REx sample return mission to asteroid 1999 RQ-36, better known as Bennu. It's expected to launch sometime in the near future, and after a 2-year journey, orbit and map the surface before touching down to retrieve 2 kilograms of material. The probe sample's return is expected in 2023. There is also a practical reason to study asteroids. In 2013, an asteroid with a mass of about 9,100 tons exploded over Chelyabinsk, Russia, with the force of 20 Hiroshima bombs, causing 1,500 injuries and damaging 7,000 buildings. It isn't the first asteroid strike on Earth, as the dinosaurs can attest to, and probably not the last. Through the United Nations, ESA and other major space agencies have established a safeguard program.
The NEOWISE data have returned two very important findings. First, we've been able to determine that we've found 93% of all the near-Earth asteroids that are out there that are larger than 1 kilometer. We've also been able to tell that there are somewhat fewer near-Earth asteroids that are larger than 100 meters than were previously thought. However, fewer does not mean none. That leaves about 15,000 asteroids larger than 100 meters that remain to be found.
This advisory group is also planning intervention missions if needed.
We think that we can cope with deflecting an asteroid with two different technologies mainly. One is what we call kinetic impactor, hitting the asteroid and pushing it out of the way. The second one is take a heavy spacecraft and use it as, say, a gravity tractor. So by the mass of the spacecraft, you pull the asteroid away.
There is one project in the planning stage to snag a small asteroid in the near-Earth region and drag it into a lunar orbit. There it can be met by astronauts aboard an Orion capsule who will study the asteroid firsthand, take extensive samples, and return to Earth. For the more we know, the better prepared we are to protect our place in the solar system.